guys, this is a question from the CF beta round 82, and the question is Buns. Here the time limit per test is 2 seconds, so you can safely perform 2 into 10 to the power 8 operation per test. And memory limit here is 256 MB. Although it's a general, but we try to be more specific to like it's optimized to 11 cache, right? Yeah. Now the question tells that Lavrenti, a baker, is going to make several buns with stuffing and sell them. Lavrenti has n gram of dough as well as m different stuffing types. The stuffing types are numbered from 1 to m. Lavrenti knows that he has ai gram left of I stuffing, and he takes exactly bi gram of stuffing I and ci gram of dough to cook a bun with I stuffing. Okay, such bun can be sold for di tuggerings. Also, he can make buns without stuffing. This is the one. Each of such buns requires C0 gram of dough, and D0 tuggerig will be earned by selling from it. So Lavrenti can cook any number of buns with different stuffing, with, without it, unless he run out of dough and a stuffing. So Lavrenti knows, basically Lavrenti throws away all excess material left after baking. Okay. So like if there is some excess material, you can say that it will be thrown away. Okay. Yeah. Basically, if this n gram of dough, you can say, is like utilized, then whatever the excess material will be there, like if they, because it's telling that it can make buns without stuffing, so it might possible that certain stuffing will get like what you call left out, so that will be thrown away. That's what it's telling. Okay, now it also telling that find the maximum number of tuggerings Lavrenti can earn. So this is the actual point here that I need to find out. Okay, so what is the input format here? The first line contains 4 integer n, m, c naught, d naught. What is c naught? C naught gram of dough will be required to make a bun without stuffing, and d naught tuggerig will be earned by selling to it. So this is what it is. Okay. And next m line we have is the m different stuffing types. Basically the details of that. ai gram left for stuffing, like how many gram of stuffing is basically that it represents. Bi is basically representing the stuffing I like amount to make one stuff. Basically, to stuff a one bun, we require bi gram for I type of stuff. Okay, ci gram of dough needed to cook, and di is basically the tuggerig earned by selling it. Okay, so like if you come to the logic part of it, you have like certain bit of thing you visualize here. That let's come to first the logic part of it. Okay, so what is given here? Basically, we are given with the n gram of dough, right? And m type of stuffing. Basically, m type of stuffing I can do basically, and here I need to prepare bun, right? Yeah. So what the question is telling that basically I have n gram of dough and I need to prepare bun. Now to prepare bun, there are two possibilities. I can either do the stuffing or I cannot do the stuffing. Okay. Now if I don't do the stuffing, then I need like C0 gram of dough to prepare one bun, and by selling it, I will earn D0 tuggerig. That is what the question is. But if I like allow to do stuffing, then if I do the I stuff, basically if I do the I type of stuff, I need that the AI, the stuff available should must be greater than the what you call the whatever the amount needed to do one stuff, that is BI obviously. And basically it requires CI gram of dough also to make the stuff, basically to prepare the bun. And by selling this, I will earn the DI tug rate. Now, the point is that if I look to the constraint here, okay, then I have something like if I just see the constraint, the n is in the range of what 10 is the power 3, m is in the range of 10, and C naught, D naught, or CI, DI, or maybe even like AB, whatever, AI, BI, that's lying in the range of 100, right? Yeah. So what I get from it that, look at this. Ultimately, I need to prepare bun, right? Yes, I need to prepare bun, and I need to utilize this basically n gram of dough. And what I need to actually find here, I need to basically maximize number of tuggery earned, right? Yeah, I need to maximize the number of tuggery earned. That's the question telling, right? So by utilizing the n gram of dough, basically, I need to completely utilize this n gram of dough, and I need to maximize the number of tuggery earned. This is what the question is telling, right? Now the point is that I can either do the stuff like this, or I cannot do this stuff. If I do this stuff, then the condition arises that it should match, like stuff should need to be available. And then it also the DOS should be enough so that I will earn the DI tag rate. But if I don't do the stuff, then there is no limit that stuff should be available. Look at this, guys. If I don't do the stuff, there is no limit that something like this, that stuff need to be available. So can we say that like the amount of the bun we prepare in which no stuff is there will be feasibly, you can say unlimited is there, we can prepare if the n amount, whatever the n amount is there, I can say that like somewhere n by c naught. Yeah, because n gram of dough is available and c naught gram of dough needed to prepare one bun. So if I say that basically if I don't do any stuffing, then n by c naught amount of bun will be prepared, right? Basically, there is no constraint that this stuff, basically actually not a stuff, we are not doing a stuff. So let's say that this is a not like not doing a stuff, so not doing a stuff, and there is no limit on the stuff available, so unlimited possibility of it could be there, can we say that? Yeah. So in general, can I say that this is a type of stuff which have the maximum limit of this n by c naught, isn't it? Exactly. This is a type of stuff which has maximum limit of n by c naught. This will prepare the bond n by c naught. Like it will prepare maximum n by c naught if we decide to not do any stuff in one of the case. Right. Yeah. Fine. So yeah, guys, what I come to the conclusion that basically if I don't decide is to do the stuff, then the maximum limit on like the case, this case in which we are not doing any stuff will be your n by c naught, right? Yeah, that is the one case. Okay, but if I decided to do the stuff, then the whatever the stuff, the maximum limit of that will be your whatever like stuff available, that is AI by the like amount needed to do one stuff, that is BI, right? So can you say that this is somewhere like, and I need to maximize the amount of Tagrik earned. Look at this. I need to maximize the amount of Tagrik earned. Can we say that? This is DI, and whatever it is, like this is the amount of Tagrik earned. If I do the I stuff, right? So if I need to maximize the amount of Tagrik earned, what the question actually is, that is the part. Here the n constraint is 10 to the power 3, right? And I need to like basically, can you say that total m plus 1 type of stuff? Why m plus 1? M is a type of stuff where you actually doing a stuff, this type. And 1 is a type of stuff where you're not doing stuff. This is unlimited, you can say, but the limit we have applied because ultimately we have a limit on the. So because of that, although we can choose this type of stuff unlimited time, but we can maximum prepare n by c naught amount of the. So that is the one part. And this one have a limit of AIBI, right? Can we say that? Yeah. This one have a limit of AIBI. That's the part. Now, this is what is the stuff. And according to the question, the limit, basically this one is 100. Yeah. 100 is the maximum like value of it. AIBICIDI range. Yeah. The maximum range of AIBICI will be 100. So if we look at it, I need to maximize the ultimately Tagri count. So it's somewhere like DP, you can say. Why? Look at a constraint here. It is lying in the range of 10 to the power 3. And the thing actually we are catching is the amount of Tagricon that is lying in the range of hundreds. Okay? Yeah. Lying in the range of 100. And the number of elements also, if I take that is m plus 1. Yeah, here the element is stuff, and that is m plus 1. And the m is actually the range of 10. So actually, let me check. Yeah, m is actually the range of 10. So since m is actually the range of 10, and the is actually we are utilizing, right? And Tagricon we are keeping, like this is the amount of Tagricon that we need to find. So can I do like certain bit of operation, like this is a part of like somewhere like knapsack? Can we say that? Yeah, it is a knapsack. Basically, you can say that this is a case of unbounded knapsack where we can take an item unlimited time, and the stuffing type is a case of bounded knapsack where we can take an item basically have a limit. Like that's why it comes under the bounded knapsack, right? But because I put the first element also have a limit, so the first element also comes in the case of bounded knapsack. So overall, this question is actually a bounded knapsack. Okay, so we concluded that the question is actually a bounded knapsack. Now, fine, up to here it's fine. Now, what could be the state here? Now the question comes that, what could be the state here? So if I talk about the state here, let me change the color a bit. Okay. So if I look for the state, let's minimize it. Okay. So here, if I look for the state, we first look at this. What is the element here? What is the element here? The element here is your bun, basically stuff type. Yeah, m plus 1 stuff type. Can we say that? Yeah. I have a m plus 1 stuff type, that's the element. So what is the state here? State here is your dpiz. Can we say that? And what is represent? Let's just minimize a bit. Yeah. This is the element, sorry. Yeah. So state here, since I need to find the maximum number of Tagrik earned. So this is the maximum number of Tagrik earned, right? By using j gram of DAW, yeah, j gram of DAW, j gram DAW up to element visited, like up to index I element visited. Can we say that? Yeah. Like basically, this is the maximum number of togric earned by using j gram of DAW up to I index visited, right? Yeah, that's what it is, and that's what it is representing. That is the state here. But guys, if this is the state, then what could be the transition state? Okay, so there are two possibilities here that for a stuff type, I will either skip it, I will not allow to do the stuff, right? Or I will take the stuff, like I will allow to do the stuff. Okay. And whenever we will allow to do the stuff, the condition will be there that there is a limit, right? I can take element multiple times, right? So whenever we take the stuff, we make sure that it should be in the maximum limit, right? We can take the element multiple times. So there are two possibilities here. That is, if I write the transition state here, then if I like skip it, if I completely skip it, okay. If I completely skip it, then whatever the case, I will I will simply go back to the previous element, and obviously here we are not utilizing any of the DAW, so DAW I value will remain same, and we need to take the overall maximum of it. So we'll take the maximum of it. Now, what will be? If I decided to take this, then what will be that? Whatever the previous state, that is previous element there, I decided to do the stuffing. So if I decided to do the stuffing, there will be definitely going to be like loss in the amount of DAW. So this is the amount of DAW needed, or you can say that cost of DAW, J minus cost of DAW, and we will definitely earn the tagrik by spending this amount. So the tagrik earned, this is what the state is, right? Basically the transition state is. Okay, fine, we look for it, but there is one more clever observation, that, or basically not a clever observation but general observation, that look at this transition state, it depends on the previous element, right? Yeah, it depends on the previous element. So since it depends on the previous element, I can optimize it even further for the L1 cache optimization, or you can say that uh, further state optimization. If I convert in the 1D, then it will simply fit in the L1 cache. So it will easy for CPU to take the element compared to RAM. So that's why we can do the further space optimization. And if you do the further state optimization, then the state will be your simply DPJ, that is maximum number or whatever the amount of tagricon, right? This is your simple like state here, and whatever the transition state, if I talk DPJ, then whatever the previous transitions, two cases will be there. Either I skip the tagric, like not tagric basically, either I skip the stuffing. So if I skip the stuffing, then it will remain same whatever the previous one, because the cost or whatever the like j is what the j is the gram, like maximum amount of tagric on by j gram of dough. Okay, this is what it is, like this is what the state is if I basically does the space optimization. So this is what the j represent here. We have on the maximum amount, that is what you need to find the tagric, but we have spent the j amount of dough for it. So that's what I'm telling. If I need to write the transition state here, there are also two possibilities. I just have done the space optimization so that it will fit in the L1 cache. So if I just skip it, it will be like DPJ. Whatever the amount of basically DAW will be not needed because you have skipped the basically skip the stuffing. So you are not utilizing like, yeah, to prepare the DAW, it will be same like previous element. You have not actually prepared the DAW, right? You just skip it. Yeah. So that's why the state will remain same. Else, and I need to find the overall maxima, so we'll keep the maxima here. And if I decided to, like, let's put the stuffing there, then obviously the whatever you can say, like, there is a DAW amount, like there is a cost here, right, to do the stuffing. And the cost is that you need to have like certain amount of DAW is there. So that is whatever the cost is there, that need to be like removed from the available like DAW. Yeah, so that will lead me to the previous state, and that's what I did here. And obviously I will going to earn Tagrik by it. So yeah, this is the Tagrik earn. So this is basically the space optimization of it that simplified in the 11 cast. Okay, yeah. And obviously there are two approaches here. One is your like tabulation, we know, and obviously the tabulation will prefer this 11 cast version because of the more space optimization. But as we know that in the like this is basically a type of stuffing, and this is a bounded knapsack. So if I use the memoization, uh, I simply like cannot have like what we can say in the memoization, like I need the this I value, like why, because memoization follow this. Why memoization basically follow this version, not the space optimization version? Because memoization use DFS for exploration, right? It is a top down version. Okay, and this tabulation is the bottom up version, so it does not care, like it will visit every basically state from the start, and it is a linear one. That's why we can simply use this 11 cast version. It will not get affected, right? Even I drop this I, right? Yeah. But if I use tabulation here, sorry, memoization here, then it cannot use this 11 cast version. The reason behind that is it is basically, I told you, use DFS. So since DFS it utilized, it is a top to down version and it is not linear. So I should know actually what is the previous state is actually coming for. So that's why in this, basically the memoization approach will follow this, not the space optimization word, right? So if I come to the code part of it, but before I come to the code part of it, there is a like since it is a bounded knapsack, right? As we concluded, like we have first I converted the one type in the bounded and make it m+1 bounded type knapsack complete question. So since it's a bounded knapsack, there is a case like basically whatever the constraint, like here, if you see the constraint, this is 100. Okay, for the like basically what I'm telling, number of times I will able to like maximum limit. Yeah, maximum limit basically. Maximum limit how many time an element I can choose, that is like in the range of 100, right? So 10 is the power 3 and somewhere in the range of 100, and you can see somewhere like I need to iterate over the m+1 elements. So m is the range of 10. Overall I can get somewhere like 10 is the power 6, so it will safely run, right? Yeah, it will safely run because I have like safely run for in general case. If I decided to iterate over like n-gram of DAW, uh, m+1 type of stuffing, and over the maximum limit of 100, right? So overall, like if I just multiply the maximum constraint, I get the 10 to the power 6. But what if the maximum limit is somewhere, let's say 10 to the power 5? If the maximum limit is 10 to the power 5, then there is something called, let's come to the next page, I tell you what. Uh, Let me tell you what it is. Okay. Yeah, guys, what I'm telling that here the maximum limit is safe, right? Here the maximum limit in the range of 100. So I can safely perform the operation in like O of basically total n gram of DAW. So n, if I calculate for all the state of n-gram of DAW, and total m plus one type of stuffing. So in the range of m on the type of stuff, if I iterate over all the stuff, and maximum limit. So if I take it somewhere like basically n is in the range of 10 to the power 3, right? Yeah, n is in the range of 10 to the power 3, and m is in the range of 10, and the maximum limit in the range of 100. So I safely conclude that it's come in the range of 10 to the power 6. And here it does not cause any problem. Our code is safely passed, right? But what if the maximum limit is, let's say, in the order of 10 to the power 5, right? If the maximum limit is in the order of 10 to the power 5, then definitely this will jump on like 10 to the power 9, and I will get TLE, right? Definitely. Overall order is TLE due to the like 10 to the power 9 order for this case, right? Yeah, in the worst case, obviously. So what comes that there is a optimization technique that we are going to use here, that is called binary optimization technique for the bounded knapsack, right? Because basically what it is, because I have a limit, right? For every element, I have limits, right? That I can take element at a certain count, right? At a certain limit, right? So what is it saying that? What is the idea here? That any number can be represented as the power of 2. Okay, power of 2 plus certain remainder. Okay, let's say the number is like 5. I can represent it as 4 plus 1. Let's say the number is 10. I can represent it as 8 plus 2. Right. So this is the logic in binary optimization. What we do here, basically, whatever the amount is there, whatever the maximum limit is there, like let's say, whatever the maximum limit is there, let's say the maximum limit is 12, I will divide it in the, let's say, groups such that it will be a sum of, like, it will be a power of 2 plus remainder. So it will be divided in the one, in one group it will contain like, I can choose, if I take that group, I will basically choose one element. Like basically I will able to, like, what you can say, I can take that type of stuff one time, then in another group it will be the power of 2, like 2 to the power 2. So it will, like, I will, if I take the another group, I will I need to bound to choose the four numbers, like four stuff together. So this is what we call, here we are doing the grouping basically. Yeah, basically we have whatever the count, whatever the maximum limit, we have broken in the groups. And what is the advantage of that? Here you can see that I can use 1 plus 4. It's come out as 5. Now I'm left out with 7. 7 is not a power of 2 and not over the next powers. It will remain 7. Okay. So what is the advantage of that? The advantage is that our complexity gets dropped. What happens? Our complexity gets dropped, that we are not bound to like go for iterate over, like whenever I am choosing an element, I'm choosing in the group. And the advantage is that I can choose any element. Okay. Like if I take the value 5, I can take 415, right? So that is the advantage, that whatever the count needed, I was getting directly, because I can choose any of the other way around, like any of the way we can choose, right? Yeah. If I need the count is 8, I will get like 7 and a 1, 8. So it will not cause problem, right? So because of that, since it is not causing problem, but the problem is that our complexity that is earlier taking maximum limit, because of the binary division, can we say that it is now O of n into m into log of binary maximum limit? Yeah. So yeah, guys, what I'm telling that the advantage of doing this binary optimization or binary deconstruction is that uh, my initially the complexity is O of n into m into maximum limit, right? Yeah, it is going in this way, right? But because of this binary deconstruction logic, because of the binary division in the bundles, my complexity now flipped to O of n into m into somewhere like binary logarithm of k, right? Yeah, or basically binary logarithm of maximum limit, you can say, if the limit is k, right? Yeah. So even if the maximum limit is in the range of 1 is to power 5, you can say, then earlier, like since n is the order of 10 is the power 3, m is the order of 10. Earlier, the maximum limit is if it is 1e5, it will get TLE. But what happened now, right? What happened now? Because of this binary logarithm of 1e5, that somewhere come out like I can say 16. Yeah, somewhere like 16 it is. So it's like 16 into somewhere like 10 is the power 4 operation per second. So it can safely run, right? Yeah. We don't get TLE as such here in this case. So that is the power of actually performing binary optimization here. So that's what we do. And that's why we prefer to like allow binary optimization. And so let's come to the code part of it. Like before I come to the code part, let's take basically the inputs here. So let me just take an input. Okay. Yeah. Let's take my templates. Okay. Yeah. Fine. Now I come to the input part of it. So we are given with n, m, c naught, d naught. Okay. Sorry, d naught. Yeah. So if I take this, let's take it. 1 second. N, m, uh, c naught, d naught. Yeah. Apart from that, I'm given with m different type of stuff details, basically AI, uh, available amount of stuff, then BI, the amount needed, like amount of stuff needed to prepare one type of do one type of stuffing, and CI will be your like amount of dough needed to do make a bun with I type of stuffing, and DI will be the tagrik earned by selling the bun. So for that, I am using a 4 containers to like store all basically m type of stuff details or whatever the if I do the I type of stuff, what are the details of it. I can utilize here a single tuple instead of 4 containers that will take the space of O of m. But I am using the 4 container, it will not much effect like the space utilized here to taking this impossibly O of 4 of m. So obviously it's not that much effect. So that's what we're doing. And now I'm taking the details of all the stuffs. Yeah. So here we are. Yeah. That's it. Yeah. Now what I did, guys, I first tell you that the this one C naught D naught. This is a I have given with a M type stuff. That is actually a M type of stuff that I'm doing. That is a limit, right? But I concluded that I have a M plus 1 type of stuff. And with a type 0, you can say that is there is no limit. But because the DAW has a limit, it has a maximum limit of n by basically C naught, right? Yeah, that's what I did, right? So what I do now to store like since to convert this unbounded one to bounded one, I need the I need the maximum limit, right? Yeah, I need the maximum limit. So what I did, since if I come to the question here, if I told you here that here to in the state I need the amount of tagrik on and do, right? Yeah, maximum amount of tag on and do is there, and how many time we are utilizing the element, that depends on the maximum limit, right? Yeah, that depends entirely on the maximum limit. So to store the maximum limit, I need, like, basically to explore the state here, I need three things, right? Maximum limit, yeah, maximum limit, amount of DAW available, right? Yeah, amount of DAW available, or like the cost, whatever the amount needed to prepare one bun, right? That will decide like whether I will able to prepare the bun or not of stuffing, right? So I need like maximum limit and cost of DAW, like for cost to basically cost of DAW I need to make one bun, and whatever the Tagrik earn, okay, Tagrik earn by like selling one bun of certain type, I type you can say. So to like gather this data, I will use a tuple here, basically a container that will store the data of all these m plus one type stuffing. So that is the first type that has a not limit is somewhere come in the unbounded knapsack, will convert it in the bounded knapsack. Okay. So I am using a tuple here to store the details of it and convert the entirely completely in m plus one bounded type element, bounded knapsack element we have. So that's what we're doing. So basically, this is the detail of stuff, right? Yeah, this is the detail of stuff, and total we have m plus one, right? So basically, let's keep it there. We'll just post back here, okay? So for the unbounded type, where we have a maximum limit is what do you call n by c naught, right? So if I just post back in the stuff, then stuff dot post back make tuple. I have a maximum limit of n by c naught. Can we say that? Yeah. And what is the cost needed? What is the DAW needed to make one bun? That is c naught, right? And what is the like Tagricon by selling it? That is d naught. So that is for the bounded type, uh, or unbounded type. Sorry. If I come to the bounded type, then here the I need to iterate over all of the m like stuff type. So I'm iterating it. Here the maximum limit, if I push back I stuff type, then the maximum limit is what? The maximum limit, if I just make tuple, put it in the tuple here, then the maximum limit is AI by BI. Can we say that? Yeah. AI amount of stuff is available, and BI amount of stuff needed to make one like do one I type stuffing one times. So the maximum times I can do stuffing is AI by BI, right? That's what I'm doing. Now I have like what you call CI amount of DAW is also needed. So this is the cost of DAW to do one time stuffing, and DI amount of Tagrik will be earned by selling this bond prepared after doing the stuffing. So this is the detail. I can pick that element, basically how many times I can perform that type of stuffing. So that will have a maximum limit of everyone. And that's why it is a question of bounded knapsack. As I already told you, now I've converted entirely. We have n plus one element, and simple that it has a maximum limit that I need to pick. So basically now it's just the bounded knapsack question. But I already told you that in bounded knapsack, I'm going to perform the binary deconstruction logic, or basically use the binary optimization logic, basically converting each of the elements in the basically elements maximum limit in the groups, divide whatever the count of elements I will divide in the groups, so that my overall complexity from O of n into m into maximum limit get converted into O of n into m into binary logarithm of maximum limit. And for that, like guys, when I get a bundle, what I'm expecting to know from the bundle, I'm expecting, because here the state is, let me write, state is DP side. what it states, this is the maximum amount of Tagrik earned, right? By like from J gram of dough. Okay, yeah, maximum amount of Tagrik earned from J gram of dough. Obviously, we have prepared certain stuffing here. So when I bundle it, what I'm expecting that I should aware of about the bundle, right? To use a bundle, I need to like basically certain cost of dough I need to give, right? Yeah. To use a bundle, I need to give a certain amount of dough, right? So I need to know that whatever the cost needed to utilize that bundle, whatever the cost of dough needed to utilize the bundle, and obviously whatever the Tagrik earned by selling that bundle, right? And obviously this maximum limit will get vanished because I am choosing now that a specific bundle, and the power of that is that using that bundle allow me that now I have one element. Basically, it is converted into one element, right? So if I do this binary optimization logic, the bundles is like a one element, you can say. And because of that, this bounded knapsack question is completely convert in the 01 knapsack question. Can we say that? Yeah, this bounded knapsack question, because there is no limit now, right? We have completely vanished the limits. And because of this bundles, the power of this is it is get converted in the 01 knapsack. So let me prepare this bundle first. So for that, I'm taking a pair here because I need to know that whatever the cost is this and whatever the Tagri code, like to utilize that bundles, right? Yeah. So here we are. We have a bundle here. Okay. Yeah. And I don't know, like whatever the, yeah, whatever the size of it, I don't know the bundle size currently. But I need to iterate over all the stuff here because to prepare the bundles, to divide all the stuffs, uh, according to like whatever the maximum limit in the bundles, I need to iterate over all the stuff. So that's what I'm doing. Total stuff is like basically stuff.size. So that's what I'm doing. Right. Now I'm using the structured binding logic over tuple so that I should not access the element using the index. So I'm directly using the structured binding logic. This I prefer because this is more convenient compared to getting every element of tuple by index. So that's what I'm doing. This is the maximum limit, you can say, right? Yeah, this is the maximum limit, you can say. The second one is your cost for one DAW, right? And this is the like Tagrik earned. Tagrik earned by selling one, right? This is your basically stuff I. Yeah, details of stuff I. Right. Now the point is that I need to prepare the bundles, right? Yeah. And whatever the bundles it is, right? Yeah. Whatever the bundles it is, the bundle size start with one. Can we say that? Yeah. And until and unless this maximum limit is greater than bundle size, or even you can say that greater than or equal to bundle size, I will keep preparing the bundles. Yeah. So when I do that in the bundle, if it is this, I'll just push back whatever the cost needed. So what is the cost needed? The bundle size into the cost of one. Can we say that? Yeah. This is the cost needed to utilize the bundle. Basically, it will utilize this amount of DAW first to give the permission to utilize this bundle, right? Yeah. And whatever the Tagri earn, that is the whatever again the bundle size into the Tagri count. Can we say that? Yeah. This is the cost. This is the cost to utilize this bundle. And this is the Tagri count by selling this bundle, right? Yeah. And obviously like I'm going to perform the binary optimization logic. So first I have like utilized this amount from the maximum limit. So since I have utilized the bundle size amount, I'll just going to subtract it. And because of the binary optimization, I will multiply the next power of 2. So that this number, whatever the maximum limit, that get represented as a power of 2 plus remainder. So that's what I did. Bundle size multiply equal to 2. That's it. And because of that, I will able to prepare the bundles for all of the stuffs. Let me see my debugger is working for bundle or not. I believe I have prepared for vector of pair debugger already. So it should work. Yeah. So you can see clearly that I have converted whatever the stuff available in the bundles. Right? Yeah. Okay. And it is representing the basically whatever the cost needed to utilize this bundle and tag earned by selling this bundle. Okay. So now my question is simple. I have like whatever the bundle dot size. Okay. Whatever the bundle dot size, I have bundle dot size element, and I can safely pick each element one times max. Right? Yeah. Each element one time max. So it's a simple what you call, since I can pick each element one time max, it's a simple converted from the bounded knapsack to 01 knapsack question. Can we say that? Yeah, it has converted from the bounded knapsack to 01 knapsack question by performing this binary optimization logic, right? So what we do in the 01 knapsack question, first I like allocate the state here, that is here dp, and like total I have to take care of the n, yeah, n gram of DOS, so n plus 1 because 0 base index, that's why. And since I'm using the maxima, so the safe value should be minus 1 is 17 for maxima, so that our value should not get affected, right? And in the base case, what is base case, guys? Base case would be your like dp0. What, using 0 gram of dough, like how many tagrik I can earn? That's 0, right? If I don't have 0 gram of dough, I will not utilize any of the stuff. So I will not able to prepare any of the bun. So obviously I will not sell. So 0 gram of dough will be formed. Basically 0 gram of dough utilized. 0 gram of dough, 0, not 0 gram, 0 tagrik will be earned because I have not sell any of the dough, right? And one more thing, that I need to give the maximum amount of tagrik on. So even if possible that I have all of the, like what you can say, I have every case, like I have even an infinite number of DAW. Every time this I have possibility that maximum amount of tagrik on will be 0 if I have not used any of the DAW, right? If I just simply skip it, yeah. So actually it's better since it is possible that because if I simply skip all the elements, then basically, because question is telling that you need to give the maximum amount of tagrik on. In that case, the maximum amount of tagrik on will be 0, right? Because I'm simply skipping. It's not forcing that I need to choose always element. I'm simply skip all the elements and I have to utilize whatever the n gram of dot there. Then what it is. Every case the answer will be 0. That's why 1 is 17 I will change to, like minus 1 is 17 I will change to 0. So that's what I did. dp dot assign whatever the n plus 1 element and simply 0. So all the cases now assigned to 0. It is feasible for this 0, right? Now since this is a 01 knapsack and I have total bundle element, I will simply iterate over all the bundle here. Okay. So bundle dot size, yeah, I plus plus, and since I am forced to choose only one element, So I'm going to use here backward loop. Look at this. First thing is that if I'm choosing a element, what is the range that is going to affect it of in the state that is of DAW? What's the range of DAW that gets affected? That is whatever the bundle utilize, cost of bundle, right? Cost of DAW that's bundle utilized to the amount of maximum DAW maximum state we are calculating. That's the same, right? This is the range that will get affected, right? Yeah, this is the range that will get affected. And since I can maximum choose one element, so I cannot use the forward loop on over all the states, because if I use, then every time whatever the new value gets calculated, that will get added. So that's why I'm using the backward loop, backward iteration. So I'm going to start with n here, because this is the range that get affected, and this should be like greater than equal to cost of bundle. Can we sell it? Yeah. And what is the cost of bundle here? That is your bundle I, you can say dot ft, the first element as you given in the pair. The first element will the cost required to use that bundle. And obviously, oh sorry, here it is ft and j minus minus, right? Yeah. Now, what is the, like, if I write the state here, then the two possibility I already discussed, that either I skip it, then the whatever the earlier state, there is no cost, like no cost to utilize the bundle, it will remain same. And if I choose it, then I need to pay the cost to use the bundle. So whatever the cost is, what is the cost here? That is again like bundle I dot ft, and obviously I have earned tagrik by selling this bundle. So what is the amount of tagrik earned that will get added in the state? So that is your bundle I.sc, as we have like taken the details of bundle, that this first element is your cost and the second element is your basically, what do you say? This is amount of tagrik earned, right? So yeah, guys, I have since calculated all the states. I need to like basically give amount of tagrik earned from the j gram of dog. So if I just simply print out, it will come out as the right answer I expect. So just do that. Spelling. Oh, basically I miss here. Like, look at this. Whatever the maximum limit, I am like converting in the power of 2 plus certain remainder, right? Every number. This is what I told, that every number can be represented as a power of 2 plus certain remainder, right? So obviously there might be a case, right, that this maximum limit have left out, like certain remainder is left out by utilizing all the power of 2. So this is simply converting for the power of 2, right? That's why I might skip one of the bundles in which like the maximum limit, what you can say, is there is a certain remainder left out after like dividing in the power of 2, right? So for that, I'm just pushing back here. So bundle dot push back. And yeah, for the braces to make the pair, very important it is. I usually forget. And here the bundle size will be maximum limit only, right? Yeah. And the cost will be simply your cost of one. And whatever the bundle size, again, that's maximum limit. And whatever the tagrik on, that will same as for the tagrik on by selling one of the bun, right? Of this type of stuff. So this is for the overall what do you call bundle, right? So now if I run, I expect the correct answer here. So yeah, now it's a correct. So this is the implementation using the tabulation approach. If I simply implement this using the memoization approach, or if I convert this in the memoization approach, then I already told you in the memoization approach, I need to utilize the factor of I also because it will use DFS. So it will explore in the non-linear fashion. So if I just convert this in the memoization approach, then I just simply have to comment this that basically, so yeah, basically 0 1 knapsack only. I have bundle dot size element. Each element I will pick one time max. After if I just utilize this overall the binary optimization logic where I have converted one unbounded one of the element into bounded one. So overall I first created the bounded knapsack of m plus 1, and then I perform the binary optimization logic. This will lead me to convert whatever the m plus 1 element have maximum limit in the bundles. So we have created what the bundles, and basically we pick one bundle one time. So this will lead me to convert the bounded knapsack into 0 1 knapsack. Now we are here at the 0 1 knapsack, and I have shown you by tabulation approach. If I go for the memoization approach, then in that case, I need to state need the factor of I, basically the previous state, basically the previous element, because we are not aware which element is previous one. Like we cannot take in the combo fashion, or we cannot take one element multiple times. So if I go random one, we are not aware that we might possible that we choose one element multiple times, and that is simply not allowed, right? So because of that, I need to know the factor of I also. So if I just give you the memo here, memo will need the factor of I. So it is like, yeah, memo. And whatever the I here, that is bundle dot size, right? Yeah. So basically, if I write the state here in the memoization approach, it is now simple 0 1 knapsack that tells that maximum amount of tagarig earned, right, from diagram of the using element up to index I. And what is element here? Element here, I simply have bundle now. So basically, that's why I put here bundle of size. Okay, yeah. And what is the maximum? Sorry, let's write it a bit clear. Bundle of size, yeah. And now the what is the maximum amount of DAW here? That is n. So I initialize the another j by maximum value is n. So since 0 best, that's why n plus 1. And since the state is not calculated, that's why minus 1. Okay. Now, if I simply write the memoization here, so let's write it. Okay. So this is memoization. I need I, right? I need J, right? J factor. Yeah, in the state. DPIJ. Apart from this, I need the details of memo. Yeah, I need the details of memo. So that's what I'm doing. Let's get the details of memo. And anything extra I need, like, yeah, I need the details of element, and that is bundle, right? So I should definitely give the bundles here. So that's what I'm doing here, giving the details of bundle. Yeah. So as we do in the memoization, first we do the pre-boundary check, right? Because we know that in the transition state, look at this here only. If I add the factor of I factor is like I told you, like let's come here. Okay, let's come here. Okay, look at this. If I just yeah, look at this. In the transition state, this I factor, what it is? It remain like always same. Yeah, I minus one, I minus one, right? So what do we do, guys? To reach to the end, uh, I need to exhaust all the element. Yeah, I need to exhaust all the element. That's why we perform post boundary check, because I is same in both the cases, right? But in J, since the value is different, in J we prefer the pre-boundary check. Basically, here I don't need to perform any pre-boundary check, but here I will especially perform the pre-boundary check, that whether this J minus cos tau is greater than or equal to 0 or not. If not, then the state is not feasible. So that's why in the memoization, here in the post boundary check, I will utilize that whether I ran out of element or not. And if I ran out of element, then I basically become 0, yeah, lesser than 0, then return 0. 0 is the safe value. In ways like maximum amount of targeting on, I told you that will be 0. So that's what it is, right? Now the base case here is that if Z is equal to 0, the base case is actually dp zz, right? The base case is actually dp00, like maximum amount of targeting on from the 0 gram of dog by visiting 0 element. But since it is for entire Z, whenever you have 0 gram of dog, maximum amount of targeting earned will be 0. So what happened, like it might possible that I have reached this for certain Z, right? That maximum amount of the earn will come out as 0, right? So since it is a top to down approach, to reach the end, it will wait. It will simply skip the element and wait to this J to become 0. So then extra call stack factor will be there, whatever the amount it will simply recursing, right? To avoid that, I simply write my base case as if J is equal to 0, return whatever the base case value, that's 0. Okay. Now memoization catch a check if the state is already known. So if the state is already known, then why you calculate, right? This is the benefit of memoization. We avoid, right? So this is what we do in memoization instead of recursion. Like if the state is known, don't calculate the states, just simply return the state. So that's what we did. We simply return the state, right? Yeah. Now, if I talk about the options here, if I talk about the option loop here, then I can either pick an element or I can either skip an element. So let's take an answer to the save value. Initialize is to 0. That is the save value I already told you. So if I skip it, then I will simply goes back to the previous element. So I will simply goes to I minus 1. J will simply will be J, and the same memo I will need to pass, and this bundle will remain same, right? But if I take this element, then I know that I just told you I need to do the pre-boundary check here, that J minus whatever the cost of dog, that is bundle I dot ft, so it must be greater than or equal to 0, so that I can reach this state safely. If it's if it is the case, then I will take the element and whatever the previous state I will go, because it's 0, 1. I cannot take one element multiple times. So I simply go to the previous state. I will pay the cost to choose the bundle, and that is your bundle I dot ft. I will give the memo. I will give the bundle here, and obviously I am going to earn target by selling this bundle. So I will add in the maximum amount of target earned. So that is your bundle dot I, bundle I dot sc. Yeah. So in this way, I will take the answer. What is the answer? Answer will be the maximum border case, because I need to give the maximum amount of the record. So that is your skip or take. Now I simply cache the result and return. So whatever it is memoize, that will be your answer. And I am simply returning the, after updating the cache, I'm simply returning it, right? So in this way, we perform the memoization over here. So if I just give you the answer here, then what will be the answer here? I'll just call This is DP, and I need like bundle dot size, but the bundle dot size amount of element is there. So what is the last index? That is -1. That's what I did. And n, and obviously here memo and bundle, and I'll simply print the answer, expecting the correct answer. So if I just do it, uh, yeah, that's what. In this way, I have implemented both memoization by this question by memoization and tabulation, and you're able to get like right. So the best part is that I can directly use this tabulation. This is more suitable because it is the one that is L1 cache optimized, because the state is like what do you call say that is one the only. So if I talk about like complexity, both will run in the n into m into log of maximum limit. I already told you, so that is fine. But since extra state, like in the state in the memoization, we are giving extra state, right? Uh, Extra allocation, right? Yeah. To avoid that, it's better here to use tabulation. So you should definitely prefer for tabulation in general. Okay. Rest is fine. Thank you for it.